Okay, start the broadcast. Go back to my view. The single page. All right.
MCTS25. That's where you need to.
Thank you. Let me see. Like this. Oops, oh. Right here. Stay as a participant. This looks good. All right, gentlemen. So welcome. Hopefully everyone is safe and sound, and it's like wintry weather we have going on. Hopefully, I know the snow and ice around me is like a lot of it is melted. You know, it started snowing yesterday and through the night, and then kind of cleared up today. You know, especially once we hit like late afternoon, it just started melting. But yeah, just be careful with Atlanta. You know, we are not used to snow, so Atlanta is like really, really hilly. So whenever you see snow and stuff like that, you want to get someplace and you get settled quick. You know, don't try to go around the city. It's a good way to sneak, come across some black ice and things of that nature. So just be careful. But yeah, hopefully everyone's doing well. Okay, so I think this past Monday was the MLK holiday. So we quote unquote lost a day, but again, this course is really structured for most of the learning to be done on your own. It's really designed. It's really designed.
They didn't have this device.
You have a question? I'll open the floor for questions momentarily. If you do have questions, feel free to.
We ain't getting no more Christmas gifts.
If you do have questions, feel free to either type it in the chat or put it in the Q&A or unmute yourself to get my attention and we'll talk about it. Let me just do the opening announcements first and then I'll open the floor. We'll open the floor for questions if you guys have any. So again, this course is designed for the learner to be done on your own. Again, anything that I want to say live is already in my pre-recorded lectures on my YouTube channel. So you can honestly use those and, watch the lectures, take notes as if you're in class, write down your questions, and either, just call or text me if you have for questions or bring them up during class and we can talk about them. Also, as you make your way through the assignments in my math lab, if you get stuck on a question, feel free to use the Ask My Instructor. That feature in my math lab, what it's going to do is take a screenshot of your question and email me a screenshot of your question. You can say, hey, professor, me and my friends were working on this. We couldn't get past this point. Can you give us some clarification? And then I'll pull it up and I'll do a dedicated video response. And then I'll load it to my YouTube and I'll send you the link directly. So that's why it's important to be subscribed to my YouTube with the notifications turned on so that when either you or your brother start asking questions, you can at least, even if you don't watch the videos, you can at least be aware of what I'm posting. Let me see. So I say that to say, so we quote unquote lost a day, but again, if you're working it the way it's designed, honestly, you could already be done with section 1.4. Now, we don't have a lot of time together. We really only have approximately an hour. Again, with my attendance is taken automatically in Zoom. It logs when you guys show up and when you leave, right? And so after each session, I'll go back and I review the attendance and I use that to. Oh, and another thing with attendance. So it's important that your Morehouse student name is showing. I had a few gentlemen that they had nicknames and things. So if it's a nickname and I think one of them was like Justin, and I'm like, yo, I got several Justin, whatever the name was. It was like I had some people that had that last name, several students that had that first name, so all I could do is throw my hands in the air. So again, it is important that your official Morehouse student name is your username for Zoom. So when I go back and take attendance, I'll say, oh, there he is, that's so-and-so. But if it's a nickname, I'm not gonna know who you are. So again, we only have about an hour together today. So we're gonna do the best that we can. We'll take approximately 20 minutes per each section. Now, obviously we need more than 20 minutes per section. But, again, whatever we don't do together, I do expect you to use my pre-recorded lectures. Again, I took my time in the past and went through as many details for each section in those pre-recorded lectures. So that's how the intent is. So again, you can honestly finish out the whole semester and then just be waiting on the exams. And then that way, this time when we're together, you can either ask questions or use this as a review session. I just do the lives just as a filler. But if enough people were like, hey, can we work on homework or something like that? I'm like, yeah, sure. We don't have to go through the material because again, anything that I would say live is already in those pre-recorded lectures. All right, let me pause for the cause there. Again, if you have questions, now is a good time. Feel free to either unmute yourself or type in the chat. I am monitoring the chat in the Q&A. So, I'll periodically, I have another device up here. So you guys start using it, I can see it. But if there aren't questions, I'm going to take approximately 20 minutes per section and just do whatever I can do in 20 minutes. Hey, Google, set a timer for 20 minutes.
Sure, 20 minutes. And we're starting now.
And again, whatever we're not able to do together, I do expect you to use my pre-recorded lectures. Okay. All right. So I think I can go like this. Nice. Okay, so we're going to continue. So I think last time we got through as much of section 1.1 together as we could. And then, the rest is left up to you. So we're going to go ahead and start with section 1.2 today. Our goal is to get through section 1.4, as regarding these. And I'll kind of want to scan and I'll just, we'll just kind of play it by ear. So with section 1.2, let me see, this is on algebraic limits and continuity. So a great place to start is just the layman's definition of when you think of the word limit, right? Push it to the limit. When you hear that phrase, what comes to mind? When you think of the phrase limit, you're trying to say, okay, what happens in the long run? If you just keep going with this concept or this pattern, how is the system supposed to behave? How can we expect the system to behave, right? So that's a decent summary of what we're going to be exploring. So we're going to be exploring functions and what happens when you push it to the limit. What happens in the long run, or what happens when you zoom in like Ant-Man into the infinitesimally small realms, right? So this is a lot of you do have to kind of use your imagination a little bit. And continuity, we're going to explore what do we mean by continuity, right? So a few objectives here. One, develop and use the limit properties to calculate limits. And then two, determine whether a function is continuous at a point, all right? I'm trying to think, what did we talk about last time? I can't think of it. So anyway, so some properties of limits, right? 1 of 4. So if the limit as x approaches a of f of x, now let me highlight this real quick. Now I think we mentioned something along these lines last time, but I just want to reiterate this notion. Again, this expression here is read, the limit as x approaches a of f of x is L, all right? So we have some function and we have some given x value a. And so we're seeing how is this function behaving as 1x gets closer and closer to that value of a, our y is getting close, is our y value getting closer to some number from either side. So I think from last time when we explored limits, we were exploring how is the function behaving as x approaches a, coming from the left and coming from the right. Okay, I think last time we said that the limit, in order for the limit to exist, the left-hand limit has to equal the right-hand limit. So as we approach this x value coming from the left and coming from the right, they have to approach the same number, right? And so I think we explored this with charts and tables. If it were coming from the left, we chose numbers that get closer and closer to our x value coming from the left, by adding on, usually it was 9s, so on and so on, right? So that was from last time. So if the limit as x approaches a of f of x is this number, L, and the limit as x approaches a of this function is m, and c is any constant, then we have the following. So the first limit property, the limit of a constant is the constant, right? So a constant is just going to be a flat horizontal line, right? If we had like y equals 3, it's a horizontal line through y equals 3, right? So no matter what a value on the x-axis you choose, you know, as other x's get closer, as we get closer and closer to that a value coming from the left or the right, the y value is always that same number c, whatever that c is, right? So the limit as x approaches a of a constant, again, it's always constant, so it's always going to be that number, right? So that's the first property, right? The limit as x approaches a of a constant is that constant, okay? Hopefully that makes sense. Again, if anything isn't clear, just stop me and we can kind of back up. The limit property number 2. The limit of a power function is the limit of the base raised to that power. So let me see. If I were to summarize it, the limit of a power function is the power of the limit, right? So let's look at it here. The limit as x approaches a of this power function is going to be the same as the limit as x approaches a of f of x, all raised to that power, right? So the limit of a power function is the power of the limit. It's almost like you can pass the limit expression into the power function, right? That's a reasonable way to like conceptualize this property, right? So the first property we had, the limit of a constant is the constant. The limit of a power function is the power of the limit. Again, it's almost like we're passing the limit function into or the limit concept into the power function, right? Which is ultimately the power of the limit. And then keep in mind that roots is another form of a power function. Because if we have the nth root of a function, that's the same as like that function raised to the power of 1 over n, right? Assuming that the limit is positive whenever n is even, because again, we can't take the even root of negative numbers. So if we have like a square root or fourth root or sixth root, any kind of even root, then we would assume, unless notified otherwise, that L is positive, right? Because we can't take the even root of a positive number. Now, if our root were odd, we can take the odd root of a negative, right? Okay, so kind of a mouthful. I know time is ticking, but you know, we're going to just play it by ear. Limit property number 3. The limit of a sum or difference is the sum or difference of the limits. So this is similar to that power, right? Kind of like how we pass that limit expression into the power function. Well, let me see. The limit of a sum is going to be the same as the sum of the limits. Or the limit of a difference is the same as the difference of the limits, right? So that's about the best way I can articulate that. So these are just some properties of limit that we're going to use to simplify some limit expressions or whatever, right? So the limit of a sum is the sum of the limits. Limit of a difference is the difference of the limits, okay? And again, this is kind of like a mouthful right now, but once you see it in action, I feel like it'll sink in. It's not as bad as it looks. The limit of a product is the product of limits, right? So we got this product here. The limit of the product can be rewritten as the product of the limit. So one limit times another limit. Again, it's almost like you're passing it through. So L times M, right? Okay, not too bad. Not too bad. More properties. This is last is slide 4. Limit property number 5. The limit of a quotient is the quotient of the limit. Similar to the previous, right? If you get the product example, then this is like a derivative of the product, right? It's similar as the previous. So the limit of a quotient is the quotient of the limits, right? And the limit of a constant times the function is the constant times the limit, right? So this is an application of like really that first one with the limit of a constant along with property number 4, you know, because you can break, if you have the limit of a constant times a function, you can rewrite this as the limit of the constant times the limit of the function. And then property 1 says the limit of a constant is just the constant. So it's that last one is just using multiple properties in one go. Okay. You can conceptualize it as like essentially factoring out that constant, right? Okay. All right, let's keep going. So now we want to use these properties to evaluate this expression, right? I'm just, in the sake of time, I'm just going to do it. I know our buzzer's about to go off, but I'm just going to go ahead and kind of do it. So I know one of them we had the limit of a sum or difference is the sum or difference of the limit. So we can rewrite this guy in the following manner. Let me adjust this. So we can rewrite this guy. Let me see. This is going to be the same as. Give me just a moment. I want to do something real quick. shift this. Oh no. Where'd it go? Where'd it go? I guess it's not gonna matter. There it is. Okay. Like that, like that, like that. Done. I don't want to do any of those. That's what I want. Perfect. Now we just want to match the size. Boom. Just repositioning it. All right. Okay. Okay. So this guy is going to be the same as the limit. It's essentially like we can distribute that limit expression, right? So the limit as x approaches 4 of x squared. I guess I'll write it like this. So plus the limit as x approaches 4 of this expression negative 3x, right? There are multiple ways we can write this. I'm just trying to keep it as simple as possible. The limit as x approaches 4 of 7. Okay, so that first expression is what, like the limit of a power function is the power of the limit. So this is going to be the same as the limit as x approaches 4 of x quantity squared. So we can evaluate that. Whatever answer we get, we're going to square that result. This next one I'm going to rewrite it. We got a constant times our function, so we can factor out that constant. So I'm going to rewrite it as negative 3 times the limit as x approaches 4 of x. Okay. And then the last one is the limit of a constant. Okay, the limit as x approaches 4 of 7. So again, that last one's the limit of a constant, right? The very first one that we talked about for today. So now, within that first set of parentheses, the limit as x approaches 4 of x, right? So it's just y equals x. So as x gets closer to 4, our y value, we simply essentially just substitute it in and plug in. As x gets closer to 4, y gets closer to 4. So essentially, that's just going to be 4 squared. The next one is going to be what? Negative 3 times 4. And the limit of a constant is the constant, so plus 7. So we quote unquote just essentially just plug them in. You know, that's an oversimplification. To be a little bit more precise, we're essentially doing what we did last time, just faster. So section 1.1, you know, we're just not writing out those tables and doing all of that. All right. Okay. So then 4 squared is what? 16 minus 12 plus 7. 7 and 4 is what? 11. So our claim is that the limit as x approaches 4 of that function is 11. Okay. So now this was us working on it together. We have some prepared notes here, right? Okay. Limit property 4. That's fine. 16. We got that. Negative 12, 7. 11, right? So they essentially did the same thing we did. I think they took a few steps or slightly different, but you know, essentially it's the same thing. I know our timer's about to go off. Limits of rational functions. And hopefully it's clear. If anything's not clear, again, either type in the chat. Let me check real quick. Chat looks good. Q&A looks good. Either type in the chat or unmute yourself to get my attention and we can talk about it. So limits of rational functions. For any rational function with a in the domain of f, for a rational function. Okay, so a rational function is what? One polynomial divided by another polynomial, provided the denominator is not equal to 0. So the limit as x approaches a of this rational function is just going to be that rational function evaluated at a. And I think that's playing on the fact that like rational functions are continuous with like no holes or gaps and no sharp edges. So it's kind of playing on that property, using that property of wait a minute, let me think. With a in the domain. Yeah, anyway. It might be a little bit off, but you know, we're good. But essentially what this is saying is if we take the limit as x approaches a of a rational function, essentially we can just evaluate that rational function at a, provided that a is in the domain of f. So an example of something where a would not be in the domain is like where a creates a 0 in the denominator. So if we're given a rational function, as long as that a doesn't create a 0 in the denominator, then we can just evaluate the rational function at a, right? But if it does create a 0 in the denominator, we have to do something a little bit different. Okay. So this is what, a power function. Okay. So we should just be able to evaluate this, right? Just plug in x equals 0. That's all I'm gonna do here. All right. So this should be, oh, here. Oh, you did? No way. There's no way that you did. So I was literally charging you before class. Okay. So I'm just going to evaluate this when x is 0. So it's going to be 0 squared minus 3 times 0 plus 2. Okay. So it's just the square root of 2. Okay. So again, all I did there was just evaluate it when x was 0. Let's see, how do we do? So the theorem on limits of rational functions and limit property 2 tells us that we can substitute to find the limit. And that's exactly what we did. Okay. I usually leave the quick checks as an exercise for you. Because again, I know my timer's about to go off. I do want to take a moment to look at this one. So now notice here, if we try to just plug in -3, I think we get 0 over 0, right? So what we're going to do first is simplify. Now we do have to keep in mind that it is a good idea to make a note that x is not equal to -3, but we can do the following. The limit as x approaches -3. Now x squared minus 9, right? That's a special factoring scenario, right? We have something squared minus something squared. For the sake of time, that factors into x minus 3 times x plus 3, right? So that's factoring, right? So then with this, now hopefully you can see this cancellation occurs. Again, keeping in mind that x is not equal to -3, but now what we're evaluating, the limit as x approaches -3 of x minus 3. Now we can use the properties like we had before. So we just plug in. So that's going to be a -3 minus 3, which is -6. So what we're saying here is that the rational function, as x approaches -3 from the left or the right, our y values approach -6. But when x is equal to -3, then it's not defined, right? I think it's a hole or a gap, right? So at -3 is not defined, it's a hole or a gap. But as we get infinitesimally close on either the left or the right, our y values get infinitesimally close to 6. And like that first class, like last week, an example here, we would have made a chart. We would have done like, okay, the left side of -3. So we would have chosen like, what? -3.1, -3.01, -3.001. And then the right side, we would have chosen like -2.9, -2.99, -2.999. And then we would see that as the x's get closer to 3 on either side, our y values get closer to -6. But this is a more sophisticated version of what we did last week. Now my alarm clock should have been going off, but I'm going to press on. Okay. Let me see. So find, oh, this is the one we just did. Yeah. -6 was good. Okay. I'm going to, oh, no, I was going to skip this one, but I like this one. I do want to do this one together. Okay, so find the limit as x approaches infinity, all right? So as x goes off to the far right, what happens here, right? Okay, so with a guy like this, what we want to do, the trick that we're going to do here, we're going to factor out x squared, okay? So this is the same as the limit as x approaches infinity. Have a question? You're okay? Okay, I think you're okay. Okay, so let's factor out x squared, right? So if we factor out x squared from the top and the bottom, notice that that's just 1, so that doesn't change our answer. We're just changing the form. So now that first expression is a 1. The next one becomes what? 4 over x, and then minus 5 over x squared. And then the bottom is the 2 plus 1 over x plus 1 over x squared, okay? So something divided by itself, this guy here in blue goes to 1. So what we're really evaluating, this is going to have the same outcome, it's just in a different form so that we can evaluate it. We have this 1 plus 4 over x, 5 over x squared. I guess my timer isn't working, I don't know. Never went off. Okay, so now with this guy, let's focus on this guy here, this 5 over x squared, all right? And we're just going to play around with some numbers to see how this expression behaves. So when x is a 1, right, 5 over 1 is just 5. What? 2? 4? Okay. So when x is 2, right, if we let x be 2, 2 squared is a 4, that's 5 over 4. When x is 3, that's 5 over 9. When x is 5, that's 5 over 25, which is a fifth. When x is 10, that's 5 over 100, right? Notice that as x is getting bigger and bigger and bigger, what's happening to our outcome is getting what? We have a fixed number over an expanding denominator. So as x goes off to infinity, that expression gets closer and closer and closer. Hopefully you're thinking 0, right? As that denominator is bigger and bigger and bigger, that expression gets smaller and smaller and smaller. So in the long run, that expression basically tends to 0. And then once you understand the concept of that one expression, this is the same concept, this is the same concept, this is the same concept. So those are 4 repeats of the same thing, right? So when as x tends to infinity, a fixed number over a large denominator is essentially 0. So in the long run, all of those expressions behave like 0, and so we're just left with 1/2. Pretty interesting, funky result, all right? Hopefully that makes sense. Okay. So that was a little trick I wanted to share there. I'm nervous about my. There it is. I was like, come on, I know you're going. Hey Google, repeat the timer. Hey Google, stop and start the timer for 20 minutes.
All right, 20 minutes added to your 20-minute timer.
Uh-oh. Hey Google, stop the timer.
Okay, cancel.
Hey Google, set a timer for 20 minutes.
Sure, 20 minutes. And we're starting now.
I just felt like it was going to do 40 minutes if I didn't make that change. So and we're actually almost done with this section. I'm just going to do a quick scan. The 1/2, and the way we did it, the 1/2 is correct, right? Conceptually. So the quick check I usually leave as an exercise. Let's look at this definition. So what do we mean by a continuous function, right? So far, we've explored the definition of the limit of a function. We said that in order for there to be a limit, the left-hand limit has to exist, the right-hand limit has to exist, and those two limits have to equal to each other. Then we say the limit is whatever that number is, right? Not only does the limit exist, but it's equal to this, right? So that's the limit definition. The limit definition says nothing about when we're at that point, right? It's only talking about when we're close on either side. So then here, we say a function f is continuous at x equals a if f of a, so the function at that point exists, so the output at a exists. The limit as x approaches a of f of x exists, so that means the left-hand limit equals the right-hand limit. And the limit as x approaches a of f of x equals f of a. So another way you can summarize continuity at a point, in order for a function to be continuous at a point, the left-hand limit exists and equals L, the right-hand limit exists and equals L, and f of a equals L. So the left-hand limit exists, the right-hand limit exists, those two limits are equal, and the function equals that number, that limit. So then that's when we say a function is continuous. It's 3 parts that you need: the left-hand limit, right-hand limit, and the value at the point. All 3 of those have to be equal to each other in order to say that a function is continuous at a point. Okay, so then a function is continuous over an interval if it's continuous at each point in that interval, right? So notice that this interval is open between C and D, which what we mean is that it's not equal to the endpoint, so we always have an infinite number of values to consider, right? If we had, I don't think we could talk about continuity at a point at the endpoint, because we won't have one of either the left-hand limit or the right-hand limit. Like if we're at the left endpoint, then we won't have the left-hand limit to compare. If we're at the right endpoint, we won't have the right-hand limit to compare. But with the interval being open, and whenever we choose a number in that open interval, we're always guaranteed to have a left-hand limit and a right-hand limit to compare, right? So the whole point behind continuity at a point, left-hand limit equals the right-hand limit equals the value at the point. All 3 of those concepts have to match up for it to be continuous at a point. Okay, I'm going to have to leave this one as an exercise. this one as well. So again, if you want to see these details, they are in my pre-recorded lecture. So we kind of are. Let me go ahead and make this available. What is the best one? Or you know what? I'll just do it at the end of class. I'll do it later. I just have to remember to come back. Okay. Okay, so let's take some time to move into section 1.3. I know we've kind of eaten into some of our time already. Let me change my view. Single page, okay. All right, and go something like this, okay. So we're continuing chapter 1, and here we're going to be looking at section 1.3, average rate of change. An oversimplification, the simplest way to summarize average rate of change is essentially the slope between 2 points, right? And pretty much average rate of change, my experience has been, is always centered around the slope between 2 points, right? So rise over run, and it's usually some articulation or derivation of that notion or concept behind the slope between 2 points. So whenever you see average rate of change, you could think, okay, slope between 2 points, and sometimes we kind of change the form of the structure, but that's essentially what it's hovering around, is the slope between 2 points. So objectives, 1, compute an average rate of change, and then 2, find a simplified difference quotient. Fair warning about difference quotient, they look more intimidating than they actually are. Again, it's really just a lot of algebra, but if you get that we're just finding the slope between 2 points, then you kind of base it there and then just kind of do the algebra, arithmetic, solving for unknowns and things of that nature, keeping track of variables. The more neat and organized you can write, the better off you are, so just kind of keep that in mind. Also, I prefer like doing homework, or especially math, like in the middle of the night when I first wake up. Right, that's just when my mind is most crisp and fresh and ready to go. Like when it's late in the afternoon, I'm getting sleepy, or I just eaten, then I can't think. I have to like get some good sleep, and then when I wake up, that's the best time. Right. So we have some definitions. As x approaches a, the limit of f of x is L is written as this, like we talked about before. Right. So the limit as x approaches a of f of x is L if all values of f of x are close to L for values of x that are sufficiently close to but not equal to a. Okay. Right? Yeah, that's fine. So this is, let me see. So again, we're saying that, let me see, are close to L for all values that are sufficient. So again, this is just a more formal definition of the limit. And we're saying that, we're saying that this limit exists. This is really just concerned with values of x that are close, that are within a certain bound of a. As long as we're within a certain, x is sufficiently close to a, then our f of x is going to be sufficiently close to L, right? And so then we're going to see, we're just trying to discover what are those bounds, how close does x need to be to a in order for f to be a certain distance from L, things of that nature. But again, limit is not really concerned with the value at the point, it's really more so concerned with how is the function behaving when x is really close to a. That's the main thing with limits. So then the average rate of change of y with respect to x, as x changes from x1 to x2, is going to be the ratio of the change in output to the change in input. In other words, the slope between 2 points, right? So average rate of change of y with respect to x, so the change in y over change in x, right? So y2 minus y1 over x2 minus x1, which is slope that we have from like all the previous courses, college algebra 1, 2, pre-cal, right? So average rate of change is just a slope. As long as x1 is not equal to x2, okay? Average rate of change. Okay, so if we look at the graph of the function, we see that the average rate of change, the change in y over change in x, which is f of x2 minus f of x1 over x2 minus x1, which is both the average rate of change and the slope of the line from P to Q. The line through P and Q is called a secant line, right? So the secant line is a line that crosses a curve at 2 points, right? So now if we look at this image on the right, we have our point P, we have our point Q. So what we're going to be exploring, right, and the coordinates for P are x1, y1, the coordinates for Q are x2, y2. So then we want to see what happens as this, on this x-axis, as this second x value gets closer and closer and closer to the first x value, right? So that's going to cause Q to get closer and closer to P. And so as Q gets closer and closer to P, once Q is like infinitesimally close to P, then we're essentially talking about a tangent line, right? Right now, we're talking about a secant line. It crosses the curve at more than 1 point, at 2 points essentially in this case. So we're just talking about the slope between those 2 points. Well, again, what we're going to be exploring is as that second x value, as x2 gets closer and closer to x1, what's happening to this secant line? It gets closer and closer to this tangent line, right? Tangent line is going to be a line that grazes a curve at 1 point. A tangent line does not cross a curve like this. A tangent line is going to graze a curve in a fashion like this. Now, if we try to find the slope of this tangent line, you know, it's a little bit deceptive because if we draw it manually, this is a tangent line, but this is also a tangent line, right? So if we try to draw the tangent line manually, you can't really get it exact, right? So we use this concept of the limit as this second x value gets closer to the first to get a better and better. The closer that second x value gets to the first one, we get a better and better approximation of the slope of the tangent line at a point. Hopefully that's sunk in because that's really what this whole calculus is about. Let me say that one more time, right? So again, with this image, right? With this image, we all know how to find the slope between 2 points, right? So what we're going to be exploring is as this second point gets closer and closer to the first point, that's going to cause Q to get closer and closer to P, right? So then as that second x value gets closer and closer to the first x value, we're going to get a better and better approximation for the slope of the tangent line at a point. Again, if we try to calculate the slope of the tangent line manually, because we can't draw that tangent line exact, we can't just draw it. So we're using this technique of the limit as that second x value gets closer to the first to get a better approximation. We're using that concept. The whole point is we're trying to find the slope of a tangent line at a point, and we're using this limit definition of the second point getting closer to the first to get the best approximation for the slope of the tangent line at a point. I know that's a mouthful, right? Hopefully it's sunk in. If not, it's going to be okay. That's essentially the whole semester, like at least 75% of the semester or 70%. We're going to be exploring concepts in and around this. And so the slope of the tangent line at a point, that's essentially called the derivative, right? And that's what the bulk of what we're going to be talking about for the semester is going to be centered around. So that's why I try to take my time to be as clear as possible around that concept of, the limit definition of that second x value getting closer to the first, yada, yada, yada. That's a little bit jumping the gun. But again, if you understand the concept of how to find a slope between 2 points, and what we're going to be exploring is the limit as that second x value gets closer and closer to the first, what slope is our function? Is this tangent line? What's the slope? What slope is the tangent line approaching, right? We're going to use a limit definition. So we're going to explore that in just a moment. Okay. So given this y value, find the average rate of change as x changes from 1 to 3. So in other words, it's asking us to find the slope, right? So given when x is 1 and x is 3, find the slope between those 2 points, right? I'll try to do it quick. Let me see. So for instance, for part A, so we'll say like, I'll call it M average, right? Average rate of change. So y2, so when x is 3, that's going to be what? 9 minus 1 over 3 minus 1. So it looks like it's at 8 over 2, which is 4. So the slope, the average rate of change as x goes from 1 to 3, we get an average rate of change of 4. In other words, I just found the slope between those two values. Okay, so for B, average rate of change, so 2 squared is going to be what? 4 minus 1 over 2 minus 1. It's going to be 3. And hopefully this makes sense. Okay. And again, I'm just finding the slope between the 2 points. For C, that's going to be what? The average rate of change, 9 minus 4 over 3 minus 2 is 5. Okay, so all I did for those scenarios, I just found the slope between the 2 points, right? Okay. So we got 4 for the first one, 3, and then 5. Okay. Man, these people are so annoying. Okay, anyway. I'm gonna leave. I usually leave the quick check as an exercise for you. The results are there if you want to practice. Okay. So the average rate of change of f with respect to x is also called the difference quotient, right? So again, remember what we described was we want to explore as that second point gets closer to the first point, as that second x value gets closer and closer to the first x value. So the way we're going to explore that, we're going to describe that second x value as x as the original x value plus some change h, right? H is some change, right? Some change in x. So we're starting with x, and the second x value is going to be the original x plus some change. Okay. So then if we're going to do, let me do it like this. So if we're going to explore average rate of change, now we just said that the average rate of change was our slope, right? So that was y2 minus y1 over x2 minus x1. But if we replace it where x1 is x and x2 is x plus some change, then it becomes the following. So y2 is going to be f of x plus h. Y1 is just going to be f of x. X2, again, was what? X plus h, and x1 was just x. So then you cancel your like terms here. So like this cancels this. And that's where this guy comes from. All right. So again, if we do average rate of change, change in y over change in x, but now our x1 is just x, and our x2 is x plus some change h. So then when you do the substitutions, eventually you get to this expression here. So where I have this blue arrow drawn, that guy is called the difference quotient. Again, all it means is the slope, the slope between 2 points, and h is just some change in x. All right, h is just some change in x. Again, this is called the difference quotient is equal to the slope of the secant line from this first point to the second point. The first point is just x comma f of x. The second point is x plus h comma f of x plus h, right? x2 is just going to be x plus h, all right? Okay, so hopefully that makes sense, right? This is kind of leading into the conclusion that we had just a moment ago, right? Again, leading up to that whole limit definition. So if you understand where the difference quotient comes from, it's just a slope between 2 points where we exchange x1 with x and x2 is exchanged with x plus h. Okay, so here, given this function, find the difference quotient when x is 5 and the change is 3. Okay, so let's do this thing. Difference quotient. Let me see, how do we, okay, come on. All right, so I'm going to start with like average rate of change. I'll probably just do one just for the sake of time. So I'll just write it as the average rate of change. So I'll start here with y2.
Yeah, we can.
I'll start with y2 minus y1 over x2 minus x1. Now, so this is going to be what? F of x plus h minus f of x. Let me clean it up just a bit. Over, basically over h, right? Because you could say x plus h minus x. It simplifies down to this. So our average rate of change, we're going to explore it as, this is called the difference quotient, this last line that I have written right now, okay? So now let's do our substitutions. So it says our x is 5, so then f of, what is that, 5 plus 3 minus f of 5 over, okay, it should just be 3. Okay, let's just keep going with that. So f of 8 is going to be what, 64 minus 25 over 3. So if that was a 30, that's 34 plus 5. Is that a 39? Is that 13?
Yep.
Okay. If I draw the box too close to a square, it makes it a square, right? Okay, I kind of do want to do the second one. I think I'm gonna do a shorthand for B. So I'll do B here, and I'm gonna use a different color. We'll do B here. Okay. Blah, 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 blah. So that's really going to be f of 5.1 minus f of 5 over 0.1. Okay. 5.1 squared. Hey, Google, what's 5.1 squared?
5.1 squared is 26.01.
So what is that? 1.01 times 10. So 10.1. Okay. All right, this looks decent. Let's see, how do we do? So 13 looks good and 10.1 looks good there. Okay. So if anything isn't clear, again, feel free to either unmute yourself to get my attention or type in the chat or the Q&A. We'll make sure to get it addressed, clear it up. Okay, let's keep moving. Okay, so for this function, find a simplified form of the difference quotient. Okay, so now when it comes to simplifying the difference quotient, first let's get a copy of the difference quotient. So that's going to be f of x plus h minus f of x all over h. Okay. So now here, we just want to basically find the simplified difference quotient of this function. So we're not given an x and an h, so it's going to be variables left over, right? So let's go ahead and do these calculations. So now, one way to kind of simplify difference quotient is to just do it in parts. Like do the f of, okay, hey Google, stop. Do the f of x plus h first by itself, you know, and then just keep tacking on each part. I think I'm just going to kind of do it in a fell swoop. So x plus h cubed. I used to know this. Let me see. So like x cubed plus 3x squared h plus 3xh squared plus h cubed. And then we got to say minus f of x, so it's going to be minus x cubed. We don't need to distribute anything there. All over h. Now, again, I just kind of did the trinomial expansion quick, you know, but again, you have to do a double FOIL to get this result. I think this is right. I'm just kind of going with it. So now, when it comes to the difference quotient, you know that you're on the right track when after your cancellations, the remaining terms all have an h. Like there's an h here, h there, h there, right? So we're gonna go ahead and factor out the h from each of those. We're gonna factor out an h, and an h. Okay. So if we do that, on top we're gonna have h times 3x squared plus 3xh plus h squared all over h. Now we get our cancellation. So again, with that second line, after cancellations, it's crucial that our remaining terms have that h. Each one has an h, so we can factor out the h from each one and they cancel, right? That happens like at least 90% of the time, right? When we're doing the simplification of difference quotients, right? So then a simplified form of the difference quotient is this result: 3x squared plus 3xh plus h squared, and that will be the result there. Okay. So remember, keep in mind that h is just some small change in x, right? So we have our original x value, and then we want to consider some change. So now that we're able to simplify the difference quotient, now what we want to do is take the limit as that change tends to 0. In other words, take the limit as h tends to 0. So like how we explored earlier, if we take the limit of this guy as h tends to 0, again, let me kind of go like this. The limit as h tends to 0, this tends to 0, this tends to 0. And so then we're just going to be left with that 3x squared, right? And that is the derivative, right? So once we start taking the limit as h tends to 0 of the difference quotient, what that's describing is the best approximation we can have for the slope of a tangent line at a point. Remember, this comes out of the slope of a secant line between 2 points, and we're considering as that second point gets closer and closer to the first. In other words, as that small change in h tends to 0, we get a better and better approximation for the slope of a tangent line at a point. So again, the limit as h tends to 0 of the difference quotient is the derivative. And that's what this whole, like at least 80% of the semester, if not more, is going to be centered around, right? And now this is the introduction of this. Once we start getting into the shortcuts, it goes faster, right? When we're doing these, simplification of the limit definition of the difference quotient, it can kind of take up the whole page and it's a little bit daunting. It can be daunting. But then in like section 1.4 or 1.5, we start to explore shortcuts. And so these calculations that take up the whole page, you honestly look at it and you get the answer. Like where we did like 3 or 4 different lines here to get that result, and we take the limit as h tends to 0, we finish with 3x squared. We're going to be able to look, given that original question, we look at it and say, oh, if you take the derivative, the 3 comes down, you subtract 1, the final answer is 3x squared, right? We're going to explore shortcuts. So to me, that's the fun stuff, right? The limit definition can be a little bit weird sometimes, but it gets easier in my opinion. Now, I don't know what you all experience on your own, but yada, yada, yada. Okay, we're almost there. So quick check I leave for you. This one, you definitely want to check it out. I'm going to have to leave it as an exercise for you. If you want to see this worked out in like an animated version, you're going to have to use my pre-recorded lecture. But that's a good one. You definitely want to check that last example out that we just skipped. Okay, and we're actually on track. Okay, so now we got a solid 20 minutes, and we'll go and I'll make a copy of these notes available once we finish out class. Let's go ahead and hop into section 1.4. And now we're on track for Monday, this upcoming Monday, to start with section 1.5. So I want to say for these first, like leading up to the midterm, we do about 4 sections a week, which is about 2 sections per session. So on Monday, our goal is to do sections 1.5 and 1.6. Wednesday is 1.7 and 1.8. I want to say once we get on the other side of the mid or exam 1, once we get on the other side of it, it gets to a point where it's, okay, 1 section per class. But for right now, we're kind of doing 2 sections per class. All right. So it's a little bit intense initially, but it does start to like taper back. Okay. So hopefully we're all aboard, and we're not all bored. I know this stuff can be kind of weird, and I know, just be grateful. Like we're only here for like a little over an hour, right? And I try to fill it in. I try to bring a little bit of funk and energy to it, because this stuff can be drab, and just be grateful I speak English. I definitely was learning some of this stuff from non-native English speakers, and they wouldn't be as clear. You would ask them questions, and man, shit was like torture.
Yeah.
So, I mean, that it is what it is, and it's not that they were wrong or anything, but it's not a lot of us, that knows this kind of stuff, or takes the time that cares to know. You know what I mean? So just try to count your blessings and take advantage of it wherever you can. Take advantage of that remote. If you haven't done so already, you definitely want to have a study buddy. Go ahead and seek out the tutors. Don't sleep on that. Just go ahead and get that system in place. Stuff of that nature. Okay, so let's try to finish this out. So, section 1.4, differentiation using limits of difference quotient. So now, this basically pulls all together that little concept that I was describing last time. Again, the derivative or differentiation is the limit definition of this. We're trying to find the slope of a tangent line at a point, and the best way we have to approximate that is the limit as h tends to 0 of the difference quotient. All right. So, because we can't find it directly, so we consider a second point. We take the limit as h tends to 0, and we explore as that second point gets closer to the first, what happens with the difference quotient, and that's going to be our best approximation for the slope of a tangent line at a point. Long story short, the derivative, we'll straighten that out. The derivative is the slope of a tangent line at a point, right? That's the oversimplification, right? So a few objectives here. One, find the derivatives and values of derivatives, and find equations of tangent lines. Again, if you don't get anything else out of this, just try to, at a minimum, the derivative is the slope of the tangent line at a point. In other words, the limit as h tends to 0 of the difference quotient. Okay, so the slope of a tangent line is going to be the limit as h tends to 0 of the difference quotient, right? So I think in the previous, we had our point P and we had our second point Q. As this change gets closer and closer to 0, the second point gets closer and closer to the first point, and we get a better and better approximation of the slope of the tangent line at a point, right? Again, manually, we can't really do it directly, so we use this limit definition to get the best approximation for the slope of the tangent line at a point. The limit is also the instantaneous rate of change of f of x at some value of x, okay? So for a function, the derivative at x is the function f prime, and so for introductory purposes, we're going to define f prime as the limit as h tends to 0 of the difference quotient, provided the limit exists. If f prime exists, then we say that f is differentiable at x, okay? So again, right, so there are a few things at play. For the limit to exist, the left-hand limit has to equal the right-hand limit. We're going to be using those limit properties to evaluate this difference quotient. So we're using like algebra along with the limit properties, things of that nature. So given this function, find f prime and then find f prime of 3 and f prime of 4. Okay, we got this. Let's start off with the limit definition of the derivative, right? So let me see. We just said a moment ago that f prime is going to be the limit as h tends to 0 of the difference quotient, which is f of x plus h minus f of x over h. Now, again, this technique is introductory purposes. When we get into section 1.5 on this upcoming Monday, all this work you see us doing, filling up the page, we're going to be able to look at the original question and write the answer. It bypasses all of this. So if this feels intimidating or whatever, just do the best you can with it. I feel like the shortcuts are a little bit easier. You can bypass a lot of this. Just do the best you can with this, right? Okay? But you can definitely do it. If you wouldn't be here if you couldn't do it. Okay? All right. So now we could do these individually, which is probably a little bit better, but I feel a little bit pressed for time. All right, so I'm just going to evaluate it. Okay? So the limit as h tends to 0. Now f of x plus h. So we got to say x plus h squared becomes what? X squared plus 2xh plus h squared. All I did was x plus h squared minus x squared all over h. Okay? So I kind of like skipped some steps, but so then if we do a simplification, this cancels this. Notice that each term still has our h. We can factor out our h from each remaining term. Okay. So then we're going to have the limit as h tends to 0. We factored out our h. Now, when we factor out h, we're going to be left with 2x plus h over h. And these guys cancel each other, which was the goal. So now we're ready to take the limit as h tends to 0. Because if we try to take the limit before being able to cancel those h's, we're going to have a 0 in the denominator, and it doesn't work. But now, because we were able to cancel the h's, now we can evaluate the limit as h tends to 0 of 2x plus h. When we evaluate the limit, this guy goes to 0. And so ultimately we get that f prime of x equals 2x. Right? So again, this was the limit definition of derivative. It kind of took up the page. Again, on Monday, we're going to explore how we can start with that question and jump straight to this answer. Like, it's real easy for the most part, right? So now that we have this derivative, okay, so then f prime of 3 is just going to be 2 times 3, which is 6. And then f prime of 4 going to be 2 times 4, which is 8. Duplicate. So what these results are telling us, we're saying that the slope of the tangent line of this function when x is 3, the slope of that tangent line is 6. The slope of the tangent line of this function when x is 4, that slope is 8. So again, the derivative is telling us the slope of the tangent line at a point, or in other words, the instantaneous rate of change at some value of x. Okay. So we got our derivative was 2x. We got the same result. Everything looks the same. F prime of 3. Oh, -6. I think I did miss. Oh, -3. I just forgot to write -3. Okay, that's fine. So this is supposed to be a -3. So that's a -6. Okay, that's good. We got a solid 10 minutes. So for this function, find f prime of x, then find. Let me do a quick scan. This is kind of a repeat. I'm actually going to bypass this one for now. If we have time, we'll come back. Quick check, I'll leave as an exercise. So for this function, find f prime. I do want to do this one. Let me just do a scan. Ooh, this is definitely a good one. Let me kind of, I might have to leave that one. We're going to come back to that. Okay, so where a function is not differentiable. So we say a function is not differentiable at a point if there's a corner at A. So like these are 3 examples of a function that's not differentiable at A. We got a sharp corner in each of these cases. Okay, because again, the derivative, we're concerned with the slope of a tangent line, and a tangent line grazes a curve. So if we have a sharp corner, then we don't have a unique tangent line, right? So we can't find a derivative at sharp corners. A function is not differentiable at a point if there's a vertical tangent line, right? So if we were to draw the curve here, the tangent line at this curve, it would become vertical, so it's not differentiable. So when the tangent line is vertical, it's not differentiable. A function is not differentiable if it's not continuous. So if there's a gap, if there's a gap or a hole, it's not differentiable. All right, because again, if you think about it from like the limit as h tends to 0, the left-hand limit has to equal the right-hand limit. I think it also has to equal the value at the point. It has to be continuous as well. Quick check. Okay. All right. So that was actually good. Let me back up and work on some of those examples that I skipped. I can do at least one, if possibly 2. All right. So for this function, find the derivative. You know what? Actually, I think I'm going to work backwards. I'm going to start with the example, the next one, this one, because it's a little bit more involved. Find f prime. Now I do kind of need some space. I think I only have enough time to do this one. This is slide 15. I would like to copy. Paste. Let me duplicate. Okay. Okay. So our function is what? 3 over x. Okay. So I think this is going to be it. All right. And we want to start with the limit definition, the limit of the difference quotient. So the limit as h tends to 0 of the difference quotient, f of x plus h minus f of x over h. Okay. And that's going to be our derivative. That's our f prime. Okay. So if we're going to evaluate f prime of x, that's going to be the limit as h tends to 0. Now we want to evaluate what? X plus h. So it's going to be what? X plus h under 3 minus 3x all over h. Okay. So that's going to be the limit as h tends to 0. Let me see. So this guy we're going to multiply by 1 in the form of x over x. This guy we're going to multiply by 1 in the form of x plus h over x plus h, 1 in this form. Okay. So then if we put these together, we're going to have what? A 3x here we're going to distribute a negative 3, so there's going to be minus 3x minus 3h. Okay, and on bottom, we're going to have x times x plus h. And if you do change flip, you also have an h here. I can just put it here, I guess. All right. Okay. So for the numerator, I got a common denominator, distributed, combined like terms. Then I had one fraction divided by another, so I did keep, change, flip, and this is where we got to. Okay, so now we get some cancellations that happen. Notice the remaining terms all have h. We can factor out that h. So just for the sake of time, this is going to cancel that. So now at this point, we have the limit as h tends to 0. On top, it looks like we have a negative 3. On bottom, it looks like we have this x times x plus h. Is that a negative 3 here? So now we can take the limit as h tends to 0. So now this guy tends to 0. And we're going to be left with negative 3 over x squared. So, that's too much. Come on, come on. Okay. So our claim is that that's our f prime, and it keeps doing that. Okay, so that's our derivative. Okay, so then they asked us to find, so that was A, f prime of 2. So then, again, that was A. So then our B, f prime of 2, is going to be a negative 3 over 2 squared. Looks like it's a negative 3 over 4. And then, finally, they asked us to find the equation of the tangent line when x is 2. So again, the slope of the tangent line is at negative 3 over 4. So if we're going to use, like for C, we can do like, we want the equation of a line y equals mx plus b, right? We have our slope, we have our x. Let's go ahead and find our y. So the slope, negative 3 over 4. Our x is 2. We don't know b. Our corresponding y. So when x is 2, our corresponding y is 3 over 2. Right? So then ultimately b is going to be equal to, looks like it's 3 over 2 plus 3 over 2. Gives us what, 6 over 2, which is 3. Okay, so we got our slope, we got our b, so the equation of our line is going to be y equals negative 3 over 4x plus 3. So what we're saying is that this should be the equation of the tangent line when x is 2. And we could graph, y equals 3 over x. We can also graph y equals negative 3 over 4x plus 3. And you should see how this line grazes our curve when x is 2, all right? Okay, let's see how do we do. I know we're kind of short on time. I'm just going to let this be it. I can get rid of this slide. Didn't need it. Delete. Okay. So we got a derivative again. The limit as h tends to 0, the difference quotient. Ultimately, we got negative 3 over x squared. I think that's the same thing that we got. So then when x is 2, f prime of 2 ended up being negative 3 over 4. And then the equation of the line y equals mx plus b, we had our slope. We had the x was 2. The corresponding y was 3 over 2. We solved for b. We got b was 3. So then the equation of the tangent line when x is 2 was y equals a negative 3 over 4x plus 3. So again, the main takeaway from this one that I want you to take is that the derivative is the slope of the tangent line at a point, right? So once you find the derivative, that is the slope. That's basically the slope, right? Okay, we did skip 2. You know what? Let's not skip it. We got over 5 minutes. We officially get out at 7:15, so I'm going to go ahead and do what I can with example 2. So for this function, find f prime of x and then find f prime of 1 and f prime of. So in other words, we want the derivative. Now I already know. Matter of fact, I think we did this already. There's an example. Where is that example? Oh, it was in the previous section. I don't want to. All right, I'll just do it just to do another demo. So we actually did this one already. We could use those results because we know that the derivative of x cubed is going to be 3x squared from before. But just for demonstration purposes, I'm going to go ahead and do the limit definition again. So then f prime of x, the limit as h tends to 0, f of x plus h minus f of x. So I'm doing this in green because it's essentially a formula, right? So I usually like to do my formulas in green. The limit as h tends to 0. So x plus h cubed ended up being x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h, right? So I think we had cancellations. This guy cancels this. We could factor out an h. I'm just going to cancel my h's. So this cancels that, and that turns into a 2. This is gone, right? So then after we do all those cancellations, we'll have the limit as, this is a repeat from, I think, the previous section. We're going to get 3x squared plus 3xh plus h squared, right? So now, when we take the limit as h tends to 0, this guy goes to 0, this guy goes to 0. So then ultimately, we're saying that f prime of x equals 3x squared, okay? So I think we did that conclusion from before in record time, okay? So then, now that we have this, f prime of negative 1, okay? So that's going to be what, a 3? And then f prime of 1.5, what is that, 3 over 2? 3 times 3 over 2 squared. 3 times 9 over 4. 27 over 4. 6, 7, 6 3/4. Let's see, how do we do? To be a speed run. So I noticed a little intense, you know, again, you just have to, let me check and make sure I did this right, and then we'll get out of here. Let's see, 3x squared is good. 3 and 6.75. Okay. All right. So we actually got through all of these examples. Okay, so I'll make a copy of these notes available momentarily. Let me just get to the end. Okay. So yeah, I'll make a copy of this available in just a moment. And again, I'll go and check attendance. So it was a little intense, you know. I can imagine there would be a lot to digest, whatever. But I tried to be as clear as possible. You know, the main takeaway here is that the whole point is we're trying to explore the slope of a tangent line at a point. If we try to manually draw the tangent line, you know, as humans, we can't get that exact because it has a little bit of wiggle room. So what we're doing is using the limit definition as a second point gets closer to the point in question. So as that second point gets closer to the first, we're getting a better and better approximation of the slope of the tangent line at a point. And long story short, the derivative, we're approximating the derivative by taking the limit as h tends to 0 of the difference quotient, all right? That's the whole crux of it. On Monday, we're going to start to explore some shortcuts on how we can essentially, quote unquote, bypass the limit definition of the derivative. And given the original function, we can just write the derivative with some of these techniques that's coming up. If there aren't any burning questions, we're going to go ahead and end the session here. So we successfully got through sections 1.4. So next week, we're trying to get through the next 4 sections, 1.5, 1.6, 1.7, 1.8. So on Monday, you can anticipate us doing sections 1.5 and 1.6. It's a good idea to go ahead and use my pre-recorded lectures to go ahead and do next week's lectures and assignments. So sections 1.5, 1.6, 1.7, 1.8. Go ahead and get all that done before Monday. So over the weekend, you want to be through sections 1.8 if possible. That way, when we come into class next week on Monday and Wednesdays, in an ideal world, that's going to be a review for you. If that's our first time, if that's the first time seeing this stuff on Monday and Wednesday, you're going to have a harder time. Versus if you get ahead of the curve, then it'll be a review at that point. Are there any burning questions? Going once, going twice? Forever hold your peas and rice, gentlemen. Okay, stay safe, stay warm, have a great weekend, and we'll meet back on Monday, same time, same place for the next installment. And for one beautiful mind to another, take care. Have a great weekend. Peace.
You too, sir.
Good video.
Yep. All right, gentlemen. And again, I'll make a copy of this available in just a moment. All right.
Excuse me.
Yes.
What sections did you say needed to be done?
So the assignments are you able to access Pearson, my math lab?
I haven't tried yet, but I should be able to.
Yeah, so idealistically, like you want to get through from sections 1.1 to 1.8. It's like 8 sections.
Oh, all right.
Yeah, but
Right.
yeah, but these assignments are listed in Pearson. Like once you get in there and you get full access, each assignment has a due date right next to it, so you can see the due date. Additionally, there's an automatic extension built into the assignments. So do the best you can. Just try to make a plan to kind of stay on top of everything.
Yeah.
You don't have to stress yourself out too much. It's just as long as you get everything submitted by the end of the semester. All assignments are unlimited attempts. I think there's only a 5% late penalty, and the system is set to take your highest score. So I just want you guys to just do your best.
All right. No, I appreciate you.
All right. First assignment, again, the due dates, if Mr. Taylor, if you're still on the call, the due dates are next to each assignment. So I know I pushed the first few assignments back by either a week or 2. So you'd have to check Pearson to see those due dates, but they're right next to each assignment. Idealistically, you want to get through from 1.1 to 1.8 before the weekend is out. So you're going to have to use my recordings to get ahead. We just finished 1.4, but if you can use those recordings and get through 1.8 by the end of the weekend, then you'll be in a good position. My internet isn't working on my phone. It's okay. Yeah, it's okay. All right, gentlemen.
Have a good one, sir.
You as well.
Well, I have a quick question. Are the videos for today on the scheduled? Is it on the Blackboard so I can go back and watch the lecture?
I load these into my YouTube channel.
Oh, okay.
Yeah,
'Cause
so if you go
on the YouTube, I only saw it was from 2022, but it's the same thing. It's not anything different.
Yeah, those pre-recorded lectures, pretty much these same topics. And then this live session, if you go to my YouTube and you go to the live, you'll see these recordings.
All right. Okay.
So
I
it's
appreciate that.
it's a combination of what we're doing in conjunction with things of the pre-recorded lectures.
I see. All right. I have a good one. Thank you, sir.
You as well, my pleasure.